When unfurled across a stadium field, the United States flag is an imposing piece of fabric. But beneath the patriotic colors is a strict geometric blueprint. Every element on this banner is governed by precise fractions, alternating arrays, and rigid proportional dimensions. This diagram illustrates the flag's exact proportions. The overall width, or fly, is exactly 1.9 times the height, and the horizontal structure is divided evenly into 13 alternating stripes. This graphic shows that because those 13 stripes are identical in size, they form a perfect unit fraction model. If you draw a flag with a full height of exactly 5 inches, the height of each individual stripe becomes precisely 5/13 of an inch. Establishing this simple fraction logic gives us a solid baseline. From here, we can apply more advanced algebraic counting methods to the most complex part of the design, the canton. This schematic breaks down the blue star field. Mathematically, it is an alternating array. This diagram shows the rows read from top to bottom, where we find 5 rows containing 6 stars, interspersed with 4 rows containing 5. This visualization asks us to change our perspective. Instead of reading horizontally, we can group the stars along exact diagonals to reveal 2 identical sets of 25. This diagram highlights 10 diagonal lines passing through the star centers. Counting the stars on these slanted lines yields a perfectly symmetrical sequence of odd numbers: 1, 3, 5, 7, 9, and then 9, 7, 5, 3, 1. This animation illustrates a core mathematical rule. Summing consecutive odd numbers always creates perfect squares. Each new odd number wraps around the previous shape to build the next square array. This diagram of our diagonal groupings shows a clean geometric decomposition. The 50 stars are arranged mathematically as 5 squared plus 5 squared. Shifting our view from straight rows to slanted lines transforms a basic counting exercise into a clear demonstration of algebraic patterns. Let's test how these numerical models apply when finding 2-dimensional area proportions. First, a quick visual test. What fraction of all the stars on the flag are located specifically in the 6-star rows? This calculation lays out the steps. We have 5 rows of 6, which gives us 30 stars. 30 out of a total 50 reduces neatly to 3/5. This slide translates our fractional dimensions into surface area. By substituting variables for the flag's overall height, we find the blue section covers 21.5% of the total canvas. The dark color in the corner commands a lot of visual weight, but multiplying the specific dimensions proves the canton takes up just over 1/5 of the flag's physical area. Finally, we can use these established proportions to explore geometric scaling rules. What happens to the math if we manufacture a flag with exactly double the height and double the length? This diagram explains the similarity rule. If every length is multiplied by a factor of k, the new area becomes k squared times the old area. Doubling the dimensions yields an area that is 4 times as large. This diagram shows that despite the repeating horizontal stripes and the ordered star array, the placement of the star field breaks the pattern, ensuring the flag has no mirror symmetry, either left to right or top to bottom. By treating a piece of fabric as a rigid object, we've decoded unit fractions, exposed alternating sequences, and mapped out square numbers. This final thought summarizes the utility of technical drawings. A math diagram serves as a functional tool to count, compare, reason, and explain.